Pedro. Good afternoon. It's a pleasure to welcome Dr. Pedro Humire Rodríguez. Thank you for accepting the invitation. He has a degree in astronomy and a master's degree in physics from the University of Concepción, and he completed his Ph.D. in astrophysics at the Max Planck Institute for Radio Astronomy in Germany, and currently he is doing a postdoctoral position at IAG University of São Paulo under the supervision of Dr. Cláudia Mendes de Oliveira. Thank you.
Okay. Thank you for inviting me. Yes, okay, good. Okay, I hope you can see it well. My name is Pedro Humire, and today I will talk about my latest work on methanol masers. It was a letter published in August this year, where we studied some low mass stellar objects, young stellar objects in our galaxy. In specific, here I am showing you CARMA 7 and CARMA 6. We observed this object and others in a total of 19 objects with the Apex telescope located in the Saint-Nectaire Plateau next to ALMA. Yeah. So to give you a brief introduction and historical information, masers were first postulated by Albert Einstein or inferred from the relativistic theory. The first maser was built by Charles Hart Townes. If you look for masers in the internet, you will see him here, also with James Gordon. So the first maser was built in the USA in 1953. And in 1964, Townes, Nikolai Basov, and Zeiger here received the Nobel Prize in Physics for the theoretical work leading to this development. Currently, masers are used for atomic clocks, for example, or also for GPS, for example, and the most common for us, the most common masers are actually the light amplification for stimulated emission of radiation, which are lasers. So this is an acronym, and now is a word for us. So in specific, and this is a bit difficult to understand, but I will try to explain you very well here. Masers are very variable in orders of days or seconds even. They correspond to very narrow line widths because they are located at certain specific coherent velocities. So they have a recession velocity very accurate with the object you are observing. So they don't have much dispersion. They are approximately Gaussian emission, quite strong, specifically as you go to lower frequencies. They are non-thermal, so they are stronger than what you will expect. And they have negative opacities. I will explain more about what does it mean negative opacity in the next slides. So the first thing you need to create a maser in laboratory or in the space, you need a pumping mechanism. It could be collisions, for example, other molecules colliding with methanol, or also infrared radiation from a star. If the molecular gas is very close to a star, the electrons in the molecules will go to the excited level due to this pumping. Then after this, here I'm showing you a similar plot. After a very low lifetime, that could be 10 to the minus 7 seconds, for example, but it depends on the Einstein A coefficient. It will go, all the electrons will stay in a metastable state that is between two energetic levels. It could be from an atom or a molecule. So all the electrons will go to the excited level, and then after the de-excitation, go to the metastable level. So they will stay here, many electrons, with more energy that that correspond to them. So they have lower energies, but they are not in the ground state. And this is what we call inverted population. So when you read about inverted population, it means that more excited molecules there are more excited molecules than molecules in the ground state. So they don't follow the Boltzmann equation. Then you have an incident photon, as you can see here also in the top rightmost panel, which is in green, representing with green, of a specific energy or frequency corresponding to this metastable state. So after this photon comes, for example, from a star, it goes to the inverted population, an atom or a molecule in red, and then it collides with all these electrons and put them away. So one incident photon will collide with an inverted populated molecule and produce two photons. And as the photons pass through the medium, the interstellar medium, you will have more and more photons of the same frequency, starting from a single photon. So this is what we call amplification. And as the photon pass through the interstellar medium, you will have this amplification. So instead of having a medium that absorbs the energy, the medium increases the intensity of the light. And that is what we assign this negative opacity. That if you see it in an equation, it makes no sense, because opacity is normally something that is obstruct the light, but for this case, it's the opposite. So for masers to be formed, you need, contrary to local thermal equilibrium, you need very specific densities and temperature ranges. For example, for methanol here, some transitions, or here, the probability to find this kind of maser in methanol, for example, these transitions, or this, depend on the gas temperature or kinetic temperature and the density of the medium. So if you have more temperature or more densities, you will reach LTE conditions, local thermodynamic. But if you are here in this part, you will see masers. Here, the color bar, the white and black, correspond to the probability to find a maser, to produce a maser. But here in the bottom, I'm showing you similar X and Y axes, but the colors correspond to the opacity. And as you can see here, the opacities are negative. So you have more negative, so strongest lines in the red part, and weaker masers in the blue part. And the lines here are some transition rates. So if you observe two transition at 104 and 84 gigahertz, and you take the ratio, you can infer the conditions of the cloud you are observing. For example, if you have this ratio, you will trace this line with the ratio and have exactly the temperature and the density of this molecular cloud. In this case, G1034. So going to the theory a bit more. So here you have the Boltzmann equation that tells us about the relation between two different states. But for masers, you have inverted populations, so N2 will be greater than N1. So if you go to the equation of the absorption coefficient, you will have this number being greater than this. So all this value will be negative. And as you have the integration over the area or the line of sight of the interstellar medium you are observing, that you are getting the absorption, you will have this value negative, so the opacity will be negative. And once you observe the intensity of the line, it will be minus, so a positive, negative opacity will lead to a stronger intensity of the line. That is mathematically what you are observing. And here I am repeating the diagram of amplification. So as the photon passes through the interstellar medium, it is the signal is amplified. So looking for some interesting practical use of methanol or in general masers, I found this, for example. This is a very famous paper, but very old as well, of 1995. Rotating disk around a supermassive black hole in NGC 4258, where you see water masers at very strong densities and temperatures of 1000 to 2000 Kelvin. For example, you can find water masers that are difficult to find on Earth due to the absorption, the telluric lines. But anyways, you can observe them, and people observe them at 22 gigahertz. And due to this, their velocities over time, they infer Keplerian disk. And with this, as time passed through, you can see, for example, a maser spot here. Then you see it here and here. So you know the velocity of the maser, specifically when they are in the plane of the sky. And you know the distance then, and the angular difference from Earth. So with this, applying trigonometry, you can know exactly the distance of the object, applying direct measurements without relying on stellar candles, for example. So with this, you can estimate the Hubble constant, for example. Also, this represented one of the first evidence of black holes here, or were very useful to study AGNs and the material around them. You can also estimate a kind of evolutionary scenario where OH, hydroxyl masers, are expected to form after a certain time, but methanol are produced in chokes, for example, or also very close to the young stellar object. So here we observe in this map, you have O2 from infrared emission at 2.2 microns, and here an inset showing you the different contours of methanol masers, and also a water maser in crosses, and the continuum emission from the object itself, methanol. So you can see also OH and methanol at the same time. So evolutionary state is a bit difficult to address. But in 2019, masers were at around 99% associated with dust continuum emission in the submillimeter. So anytime you see masers that are very strong and easy to detect, you will determine if they are at this frequency that correspond to class 2 to young stellar object being formed. So it's another tool to detect very young regions in our galaxy. And here you have the association of 90%. Also here in black, there are the whole sample of around 1,000 objects in our Milky Way with the Atlas Gal survey. And you can see that masers are formed at certain specific ages. So in green, you see the methanol masers that are initially not detected, but then after this range of volumetric luminosity over mass, specific mass, you can see them. And this means that you need some certain mass of the protostellar core. Then you can also see H2 regions overlapped with the emergence of masers. As you can see also here in the beam diagram, here in the left you have a circle with the methanol masers, and to the right the H2 regions. So you have a certain amount of sources with showing both H2 regions and methanol masers. And then after certain specific mass, maser emission declines due to H2 regions disrupting the environment, and the H2 regions themselves become extended. So if you observe them, you know more or less that they are occurring at certain period of the cloud. Going a bit more through and with more nicer slides, you can here you have an evolutionary phase of all the clouds, and the methanol maser are expected to emerge in this specific range. Then you have H2 regions, ultra compact H2 regions called collapsing cores and hot molecular cores. So a couple of authors already presented some diagrams for evolution, so, like Reid and Ellingsen, but they need to be confirmed. So first you expect to see class 1 methanol masers that are pumped by chokes, then class 2 that are pumped by infrared emission from the star, more evolved, then water masers, hydroxyl masers, ultra compact H2 regions, and some overlapping. And the same from Reid in this part, although a bit different. Also, finally, one last possibility that something you can do with masers are water mega masers that are 1 million times stronger than what normally you see in our galaxy. With this, you can apply this trigonometry to create a Hubble diagram with distance, as you will have the distance and the frame velocity, and determine the Hubble constant or the Hubble parameter over on cosmic scales. And over time, people are discovering more and more water masers outside the Milky Way. Talking now about methanol, so to then combine them and talk about methanol masers, they are formed in dust, in grain dust, starting from CO, carbon monoxide. Then the grain attracts some hydrogen, and over time you will create a methanol, and then being very close to a star, a young stellar object here. So first you have some molecules cold, and then methanol, for example, is going from the dust to the gas phase, and you can observe them in radio. So, and we call, when they have more than 5 atoms, we call them those molecules complex organic molecules. So you will expect to see them after a temperature of 200 K. And for destruction, you will expect to destroy methanol when you have a lot of cosmic rays, and also very strong shocks. And we try to observe that empirically with our data. As methanol, this is the molecule of methanol. You have the hydroxyl and the methyl group here. They have a torsion, so they have plenty of emissions due to that, since the Hamiltonian or the equation that explains this molecule is very complex. Actually, I am showing here very simplistic Hamiltonian, but in reality it could be a table of 2 pages of formula. So you have in LTE alone, without being maser, methanol can tell us about the gas density, the infrared radiation, and the kinetic temperature when you observe vibrational excited transition. And due to the distortion, you have this parameter here that produce more lines. For example, I detected more than 150 lines in this range of frequencies. And you have two types of methanol, methanol E and methanol A. Methanol A occurs when you have all the 3 hydrogens in the methyl group, which is this here, with the same spin. And when one of the spins of the electrons in the hydrogen of this group is opposite to the others, counter-rotating, you have methanol E. And there are 2 types of methanol E. So summarizing, talking about masers and methanol, you have 2 types. The class 1 that are collisionally pumped. So these collisions produce the pumping to produce the excited level and then the excitation and maser. And class 2 is produced by infrared radiation. So the infrared produces this pumping to produce the excited and then the inverted population. The class 1 is produced by shocks in protostellar outflows, but some people also detect them in limb resonances, for example, or other phenomena. And they trace very early stages of star formation and are also detected in low mass stars. While class 2 are pumped by infrared radiation associated with high mass young stellar objects. As they need the infrared radiation, they are very close to the star. So you know almost exactly the position of the young stellar object. And this is the 6.7 GHz line. And they are exclusively observed in high mass star forming regions. So to date, all these transitions were detected that I will show you here. For class 1 only, we will focus on class 1. There are many as of 2016, but looking at this diagram where the transitions producing masers are in red, in LTE are in green, and absorbed, so you can also have absorption, are in blue. There are some transitions that are not detected so far. This is specifically the 7 to 6 and the 10 to 9. So I was wondering whether these transitions were we were able to detect them. As you go to higher frequencies, they are more difficult to detect because the lifetime of the excited level is lower, and this is difficult to detect because, well, both are in the range of water absorption due to the atmosphere. So with a couple of friends at the Max Planck, at the end of 2022, we proposed to observe a survey of low mass young stellar objects. Gisela, they both were doing the postdoc, and now they have permanent position in Mexico. Gisela in Inahue and Antonio in the Technology Institute of Monterrey, and we use the Apex telescope. The sample consisted in 20 or 19 sources, because one of them were very close to the other due to the beam. One of them is very famous for other studies. People are detecting more and more molecules over time in this young stellar objects, because it is very bright and not so far from us, as you can see here. It is located in the Perseus arm, looking at the center of the Milky Way. So here you see a panoramic view of the central regions of the Milky Way and the Ophiuchus star-forming regions. You have this ERAS 16223 in this location, and people detected recently this molecule in this object. The original idea is to look for water masers at higher frequencies. So most of them have water maser at 22 GHz, but we don't know if we can observe them at 325 or 181. And that can tell us about the density of the molecules, of the cloud. So talking about the specific transitions I show you that are lacking, the lowest frequencies, the ones that are here, were detected from the 80s, 90s, and 2000. So every 10 years, people detect a new transition with more frequency. So, for example, Morimoto detected in 1985 the first detection of these frequencies. Then Bartla and Menten. Then 10 years later, Slish detected the transition at 132 and 229. This number here is the J that you can replace here. So this is 4 sub minus 2, 3 sub 0 E, and so on. So the latest transition was detected exactly 10 years ago, and now we plan to detect the others. Yeah. Yes, B0. It's not vibrational. Yes. So when I was very interested in this specific, you will wonder why these specific transitions. Why the class E methanol masers are, class E methanol in general is emit at lower temperatures and densities, so it's more easy to find. And for example, here you have even no continuum emission at 1.3 millimeters, but you can still see methanol. So you could detect and infer some conditions of the ISM using maser emission instead of the continuum, even before the star is visible for us. So they detect, for example, Seng observed that, and detected. People think that with more sensitivity, telescope will be able to detect the continuum of the star in the future. The other reason I am interested in this transition is that in the past I studied the central molecular zone of a nearby starburst, and we detected the same family series, the same transitions at the outskirt of the central molecular zone at around 300 parsec from the center, and is where you see the Limblom resonances that are the ellipses here. So this means that when you have the spirals colliding with the inner bar, you will see the methanol masers in these specific ranges, in these specific families. Here I also compare the 84 GHz maser to LTE conditions, obtain the ratio, and this is the ratio in colors. The same color code is in the left and in the right. And as I mentioned, methanol is formed in dust, but then can be destroyed for photodissociation. So one way to measure photodissociation is Cn over C17O. Well, C17O tells us about the mass, so it's a kind of normalization. And here SIO over HNCO tells us about the Chocs strength. So when you have more SIO, you have stronger shocks. When you have HNCO, you have weaker shocks at about up to 30 kilometers per second for HNCO. So if SIO is too strong compared to the weak shocks, you will not see masers. And also if you have photodissociation, you will not see this kind of masers. So all of them are here in the out here. Because you have very strong, due to the very strong star formation rate in the center, you have a lot of photodissociation here, also traced by C2H, for example. So, but the problem of observing these transitions I mentioned, I was looking for in another galaxy, like in NGC253, is that the lines are very weak, very broad, like 100 kilometers per second or 800 kilometers per second. Here I show you the transition I was looking, but it is completely blended with ancient J-1. So it is impossible to observe them beyond the Milky Way. Also, you need very dry atmosphere. These are in the rightmost panel I show you the atmospheric transmission. So you have, for example, a 2 millimeter of precipitable water vapor. You have only about 20% of transmission. But if you have 0.5, you will reach about 50%. So you can see the line. But for this, you have like 20 days in ALMA to observe that. So extragalactic sources have larger line width, lower linear resolutions, more line blending. Due to this lower linear resolution, you are combining everything. But galactic sources have normally a full width of around 10 kilometers per second. So here I did some Gaussians with 10 or 15 kilometers per second, so you can see the lines separated. And for example, for CARMA 7, we completely isolated the line. Here I show you the same lines, the methanol line and the HNC lines, completely separated in our sample, in our galactic sample. So we can determine the maser nature. One way there are two methods to detect masers, at least two. Rotation diagrams that are here, and radiative transfer equations, models. So if the lines are in LT conditions, you will expect a behavior like inside the slopes, with the green transitions are LT. Then there are also lines that are not maser, but are also not following LT. We call them quasi-thermal emission in blue. And the transitions I was looking for they have negative opacities and negative excitation temperatures, and they are in red. So we detected transitions, methanol masers, in 5 out of the 19 sources. Some of them were both of them detected. Sometimes only the higher frequency transition was detected. And then we continue for CARMA 7 specifically with the radiative transfer models, using 3 different components. Total fit in red. The green line represents the non-LT, so the closer to maser, and blue line the LT component. So most of the line follow LT conditions, as the blue line is co-special with the total emission in red, but some of them, the quasi-thermal emission transitions, need also a very important contribution from non-LT, and finally the masers are not reproduced, like this or this other. And this is how you see methanol masers in sub-millimeter. Normally they are very strong, but they are at very high frequency, so they are more difficult to detect. And here I show you the same image I showed you at the beginning of CARMA 7. Also you have a contribution of CARMA 6 and the apex beam. So at 181 gigahertz, you have a beam that also have the contribution of the companion, the CARMA 6, but at 325 gigahertz, you have a lower, better resolution, angular resolution, and you can determine that all the emission is coming from the CARMA 7. So this line is completely from CARMA 7, and this gives us more argument that this line is also coming from CARMA 7, also due to the systemic velocity. So these beams are in orange, are the lines in orange here in the orange area, and in magenta are the others are here. We feed them, finally we feed them with 3 different components. One non-LT component aiming to reproduce the Maser conditions that are in the shock fronts of the outflows, the stellar outflows here. Then a narrow component that try to emulate the conditions of the continuum image at 1.3 millimeter, the continuum emission. And finally, a broad component that represents the very cold gas that is surrounding the object. So combining all of them, we have the profile. We can reproduce the profile with the broad component more easily seen here, for example, and the narrow component in the points, in the peak of the lines. And then we can also compare with what we observe in AGC-253. For example, we have much lower full widths or higher temperatures, kinetic temperatures than before, because we are very close, so we can determine better the temperatures and other parameters. Apart from that, we compare. There are not many studies looking for low mass stars. Normally, people look for the strongest masers in high mass stars, but it's practical to observe low mass because they are closer to us normally. They are more numerous. And we found that the relation previously discovered by Kalensky is not following for us for this kind of maser at least. So the volumetric luminosities of the source is not correlated with the luminosity of the maser. And finally, we detected the 2 transitions. So, and these are the conclusions. Okay.
Questions?
Very interesting, thanks. You made these observations with APEX, right?
Yes.
But as you know, LLAMA, one of the projects for LLAMA, one of the major projects in the science case of LLAMA will be the detection of masers. So do you believe that making baseline interferometry between APEX and LLAMA will help to extend your sample to neighbor objects, galaxies? It would be enough?
We will have to do the calculations.
Of course. But
because, yeah, with the interferometry, the problem is that we have flux missing flux problem.
Right.
You don't capture all the emission, normally only the very, very strongest points. So the sources could be smaller than we see with APEX alone. But with JAMA alone, we will have maybe more time and we can extend the source.
of course.
The sample. We could observe hundreds of objects with more time. That is
Right.
something for sure. Yes.
Thank you. I'm not from the field, and I'd like to understand some basic aspects. For example, what's the relevance of this detection in terms of knowledge concerning star rate formation, for example?
Yeah, well, as you can see in the tables, we obtain some parameters that are very accurate, like difficult to detect. But you need more and more transitions to, for example, if you have only 2 transitions, you can determine different densities and temperatures. The problem is degenerated, and you will not have the exact single result.
But can't you learn the same thing with other transitions?
For non-LT, not, I would say. For non-LT, because for masers, you are out of LT, you have the continuum, the kinetic temperature. You have this diagrams I show this. So with 2 maser transitions, you can obtain exactly the kinetic, not the excitation temperature. Normally, you have with radioactive transfer the excitation temperature that is not necessarily the gas temperature. It's the Boltzmann, is the temperature in the Boltzmann equation. So you don't know if this temperature is the real temperature of the source. But with masers with non-LT, you have the kinetic temperature.
And the last point, could you please say a little bit more about using masers for cosmology?
Cosmology? Well, it's not not much field, but all are based on this. So you know they are water masers, and if you have this, they are very strong and can be detected with interferometry. So you have up to the most recent paper as of 2022 reached about 20 microarc seconds. So with this you have a lot of resolution for linear angular resolution. The velocity here you know the velocities, and you can assume this velocity is the same here and the same here. So the time that takes this maser spot to go from here to here, you know the distance and you know the angle. So you know with trigonometry you know the distance to the source. Yeah, you can assume a triangle like isosceles triangle.
I was just wondering if this could be as accurate as type 1 supernovae, for example.
It's better than type 1 supernova. Yeah, you know, direct, you don't need to rely on any other method, only trigonometry, and you have these very low error bars. The problem is to identify water masers outside. Yeah. Yes.
My question was very similar to the colleague. Do you know what's the range of distances where you can use masers for distance determinations?
This?
Yeah,
this is the latest.
Is that all you can do,
Yeah.
or you can go
Yeah,
further away?
This project, I went to the web page. There are like 10 people only. This is the most distance you can, 125 megapads.
Okay.
Yeah, I don't know. I am not sure. They have here. So they are having used in ATCA. They don't have ALMA here. Maybe with ALMA it will be better. Yeah.
Syriaco?
Yes, hi, Pedro. It's Syriaco. Nice to see you talk on business here at the IAG. Can you hear me? Yes?
Yes.
Okay, good. I have a couple of questions. So you show that it has been proposed that there's a correlation between the luminosity of class 1 methanol masers and the barometric luminosity of the region.
Yeah.
And that is based on 44 years observations.
Yes.
I'm not sure.
Yes.
But your data points don't seem to follow that. So are you planning to target these lines in other regions, for example, high mass Earth-forming regions, to assess if the correlation actually exists?
Yeah, that will be a good idea. The fact I use only low mass is because the original idea was to look for water masers in low mass that are not very well constrained. But for methanol, yeah, we could do the same.
Yeah, that would be nice and useful. And the second quick question is, since these class 1 masers are excited in shocks, as you said, one good usage for them would be to use them as probes of kinematics. So do you have enough sensitivity in your apex data to detect high velocities?
No, you
do you see any wing or something that can tell you that there is an outflow there?
No. The problem with the masers is that you can, at most, 60 kilometers per second away from the source velocity. Masers are normally for class 2. For sure, only for the velocity of the source, but also class. I don't have an image here. Well, this one. When you observe the masers, you observe the maser arising from the plane of the sky. So the velocity is more or less the velocity of the source. There are only a couple of cases when people detected maser at more than 80 kilometers per second from the source velocity. But this is because the outflow probably is choking with a molecular cloud that is next to it. But in order to have coherent emission, same velocity, same frequencies, you are detecting the maser on the plane of the sky. So not much misalignment with there are people observing SIO over tracing the shocks over against the masers, methanol class 1 masers. But they don't find more than 60 kilometers per second away.
So you were just, let's say, unlucky with the inclination of your source, or do you think that with single dish getting high velocities, since you have less coherence and so less amplification, so the emission is weaker, is basically hopeless? I'm just wondering if you need to go to an interferometer like ALMA to get a nice spectral profile that can cover also the high velocities.
Yeah, the problem is that if you, for example, try to trace the shocks in the plane of in the line of sight, you have very few maser spots, and you cannot see them. You only see them when they are in the plane of the sky.
Yeah, sure.
You sum over all the emission. That's
right.
Yeah,
all right, thank you.
Okay.
More questions? No? Thank you again, Pedro.
Okay.